All right. Thank you for coming to class today. I apologize for being a few minutes late. I'm just amazed with the rain and all that. I figured I'm going to be talking to myself, but no, you guys are here, so that's great. Thank you so much. I'm always grateful to have an audience. You know, the reason why they film comedy with a live audience is because a live audience makes, you know, the show better. And it's great that you guys still come to class, because I'm certain my presentation, which isn't very good, it's better because you're here. Okay, so we've been talking about reward and effort and how these commodities, these economic things, affect the way the brain makes movements. So I have a lot of feedback in my ear from this, maybe it's the speakers or something, but I don't know if they're different than usual. I'm not sure what's going on. Thank you so much for looking into it. Today I want to talk about reaction, how we react to stimuli. And, oh, much better. So the period of reaction time is a period where your brain is evaluating your options and deciding on what to do. And I want to show you a mathematical way for us to think about the period of reaction time as a period of deliberation between options. And we're going to talk about how utility, which is this concept of describes the goodness of this option that we have in mind, which incorporates reward, effort, and time, how that can be used to understand what reaction time is about, which is a period during which you integrate the evidence for the various options that you have, and then you make a decision of what to do. So you can think about reaction time in a broad sense is when you have a decision to make, where to go to college, who to marry, whatever, which house to buy, which car to buy. And you may take a long time to come to your decision. But during that period, you are integrating the evidence associated with each option and coming to a decision. Well, a simple movement, like moving your eyes to a stimulus, is also a decision that you're making. Like on Wednesday, when I presented you with 4 images, your brain made a decision where to take my eye. And then you made a decision to move your eye to a particular location. During that period, what was happening in the brain? It was a period of decision making, considering the various options. So today I want to talk about that period. It takes only 200 milliseconds to make that period, so that your typical reaction time is extremely short. But nevertheless, it's going to teach us something about decision making in principle and how the brain goes about making decisions in order to make a movement. And then we're going to link that to the concept of utility, because it's not just that you move faster towards stimuli that you value more, you move sooner, meaning that your reaction time is shorter for stimuli that you value more. If you have a face to look at, you move earlier toward the face and with higher velocity. So we want to understand that kind of data. In order for us to get there, we need mathematics. We need to have an expression that says, well, what's going on? And then once we understand the mathematical representations, then on Monday, we'll talk about the brain. How does this process of integrating evidence take place? Okay, so let's begin with a simple experiment. A light goes on, and you're supposed to move as soon as the light goes on. You're in a dim room, and when the light goes on, you know, you see it, and then you move toward it. Just say you move your arm toward it. Now, the intensity of the light is what they varied in this particular experiment, and the data is shown here. So as the light intensity increases, you see that the reaction time decreases. So this is from 140 years ago, where this paper was published, and you see that basically the brighter the light is, the earlier the movement is made. The movement is on the order of 180 to about 300 milliseconds in reaction time. So this is before the movement starts. So the person reacts sooner when the stimulus is brighter. Okay? That's maybe isn't surprising. Maybe somehow that, you know, amount of light reaches some kind of a threshold earlier because you see it sooner, perhaps. But we'll talk about what that means. The other important aspect of this data, however, is shown here, where you look at the statistics of that reaction time. We're going to look at the mean here and the median. And it turns out that the median is smaller than the mean, which means that the distribution of the reaction time has a big tail. There's a whole lot of times when the person makes the movement pretty late. And so that distribution is going to be important because it's going to teach us something about this process of what's going on during the reaction time. Today, it's about thinking about random variables, distribution of random variables. What does it mean to have integration of random variables to a threshold? And then once we figure out the math, we'll look at how it relates to the process of making a movement and the brain. All right. So here's a simple task. There's a fixation point. This is the time on the x-axis. The fixation point is on during this whole time. And then at some point the target goes on, and then the eye makes a saccade to that target. So very simple. You're looking at a dot here, the dot is there, another dot appears, this dot still is there, you make a saccade to it when the second dot appears, the target appears. And here's the distribution of the reaction times, how long it takes. So the dot is always the same intensity. What you notice is that there's this distribution, and the distribution has a tail that's kind of long. And if you look at things like the mean and the median of it, you see that the mean is a little bit bigger than the median. So this is a typical kind of data associated with reaction time. If you bring a person to a laboratory, bring an animal to a laboratory, give them a stimulus and ask them to move when they see the stimulus, or hear a stimulus, or feel a stimulus, they're going to have a reaction time that's going to have a distribution that has a long tail. Why? What does that tell us about the process of starting a movement? Why does it have a long tail? So that's the first question that I want to answer for you. So people have thought about this, and people have been thinking about, well, what might be going on during this process of waiting until you make a movement? So the important thing is to know is that it's not that it takes 200 milliseconds for the light to reach the information about the light to reach your brain. That is not the case. Because we know that at 70, 80 milliseconds after the light falls on the fovea, you have information about the light on the superior colliculus. But then from that time to the time when the saccade starts, there's this deliberation going on, evaluation going on, and that's what that time is taken up. And then you make a movement. So the early models viewed this process as a process of integrating the spikes that are coming down the axon, and then you're saying, once I get enough spikes, I have somehow reached a threshold, and then I will make a movement. So here's the random variable R, which is rising with this rate that at some point is going to get to threshold. And if this line with this slope R is a random variable that can sometimes be steep, sometimes be shallow, you notice that it will generate a response that will reach when it reaches threshold. So here's when the stimulus comes, and then there's something that is integrating the evidence for the stimulus at some rate. Sometimes that rate is high, sometimes the rate is low, sometimes it has this mean. When it reaches threshold, it will generate a movement. So you can have an early times when it reaches threshold, you can have it reach very late. On average, it will reach at this time. But you notice that it's going to have this distribution that's going to be skewed a little bit to the left of the mean, but a great deal to the right of the mean. So it's going to look like this. Here's the distribution of the latency. It's going to have a skewed distribution. So if you have a process where you are integrating something, so you see you adding until it reaches threshold, and then you go, then the randomness in that integration process, sometimes it's steep, sometimes it's shallow. You will get to threshold early or late. And if you look at the distribution of when it gets to threshold, it's going to have this kind of a distribution. So in the models that began this world of decision making and how a movement starts, what they imagine is that sensory information is arriving at a particular rate. Say the light. The light is on and it's giving the brain information. And then the brain is accumulating that information, and it's going to go when it reaches a threshold. So if you have two options, you are accumulating the goodness of this option against this option. And when the first one reaches threshold, you move toward that particular option. This kind of process of integration of evidence to threshold would give you a distribution of reaction times that have that long tail. So if you have something that you have a rapid rise, you're going to get a distribution that looks like this. If you're going to have something that you have a shallow rise, you're going to have a distribution that looks like this. And so what I mean is that the rise rate has a mean that's described by this R. This mean is small. This mean is large. And so if there is variability from trial to trial in this rate, then the result will give you variability in when the movement starts. And that variability will give you a distribution of when the movement starts. And that would be the reaction time distribution. Let me stop for a second. Do you have any questions? Yeah.
So what exactly is causing the variability in the threshold?
Right. No, not in the threshold.
Or
in the rise.
Yeah,
in the rise rate. Unknown. It's a stochastic variable. For whatever reason, sometimes it's a little bit higher, sometimes it's a little bit lower. And we will look at the alternate hypothesis of what happens if the threshold is a random variable. Okay. All right. So here's our problem. You have something that you integrated. We call that the merit of performing this action. And let's call that x, which is rising and falling through accumulation of evidence. There's a threshold for performing this action. It's called that x star. So x star is up here. X has to rise until it gets to x star. And when it gets to x star, you're going to go. Once the merit of moving to a particular location reaches the threshold value, that movement is performed. The merit of this action has a rate that's specified by R. And so the larger the rate, the sooner the merit of that action will reach threshold, triggering the movement. Therefore, in this model, the reaction time is the latency from presentation of the stimulus to the time t that the merit signal x reaches the threshold. So x is rising with some rate r until it reaches threshold x star. The time it takes to get there is the reaction time. All right, now what we want to know is that what's the distribution of the reaction time with respect to the distribution of the rise variable r. So that's what we want to know. Okay, so during the reaction time, you're accumulating the merit of making the movement there. Just like making a decision toward, what to do. You are accumulating evidence for the various actions until it reaches threshold. Whichever gets there is going to be the winner. So to explain the relationship between rate of rise r and the reaction time t, we're going to use probability theory. We're going to say the probability density of r, which was how fast this thing is rising. Sometimes it's rising shallow. Sometimes it's rising rapidly. We're going to represent with a density function. We're going to call P of r. We're going to have another density which describes the time, so which is going to be our reaction time. So our reaction time is going to have some shape. That's the probability density of the time when the movement is going to begin. That's going to be P of t. And we're going to have some starting position. So our merit is x0, which means basically at time 0, how much prior knowledge I have about where the stimulus is going to appear. So if you can completely predict where it's going to be and when it's going to be, you don't need any evidence for it. You can just get there. So x0 is the initial conditions for the merit of performing the movement. And you're going to have to get to threshold, x star. So here's how much time it's going to take you to get there. You're going to need to get to x star. You're going to start at x0. You're going to rise with the variable r. And the simple division tells you how long it took you. But here's the interesting part. T is a random variable. R is a random variable. What we want to know is what's the distribution of t given the distribution of r. What's the relationship between the distribution of the reaction time and the distribution of this variable r? Yes, sir?
Why is it reasonable in this case to assume that r is a constant and not a function of time, for example?
Right. So in this case, we're assuming that during a single reaction time, r is a constant. But it's a random variable between trials. more sophisticated models have R itself be a random variable during a trial. So one could consider that as well. Yeah, good question. Okay, what we want to know is what's the probability density for the random variable t, which is the reaction time. All right, so to do this, I need to teach you about algebra of random variables. So keep in mind, well, why are we doing this? Why is this guy pushing me down this road? What's the goal here? What I want to show you is why is it that you react faster to a more valuable stimulus. That's where we want to go. And to get us there, I need to show you how you do calculus of random variables. So just a little bit of math that we're going to need to get our end that we're seeking. So let me show you a little bit about algebra of random variables. So what we want to know is that we have a random variable x, which is described by a probability density function, which we call px. And we know there's another random variable y that's related to x. In this case, it's linearly related. Y is equal to ax. If I gave you the probability distribution for x, what would be the probability distribution for y? So if x is your random variable that you have a distribution for, and y is related to x, what's the probability distribution for y? So why am I giving you this? Because what we want to know is that t, time it takes to react, is related to r. R is a random variable. How does t, what's the probability distribution of t? But in order for us to get there, let's do a simpler case. Let's say y is equal to ax. All right, so here's y on this axis. Here's x here. So when I want to know what's the probability of y, so random variable capital Y, what's the probability of it being less than or equal to little y? So here's y. Say it's here. What's the probability of it being less than or equal to this number here, which is this range? So what's the probability of y being less than this, which is this range here? Well, that's equal to the probability of x being less than this, 2, less than that. So probability of capital Y, the random variable y, being less than some arbitrary thing y, is the same as the probability of random variable x being less than y divided by a, because y is equal to ax. Let me stop for a second to see if you can look at that and see if that makes sense. All right. So let's call this capital P of y and capital P of x. The probability of y when it's less than some random thing, little y, and probability of x when it's less than some little thing, random variable x. Okay. So how are these things related? So here's where we had our definition. And, well, the probability of random variable capital Y being less than some amount little y is the same as the probability of random variable x being less than some amount little y divided by a. So what's the probability density of y? Well, probability density is the derivative of the probability with respect to the random variable y. So capital P is the probability. Little p is the probability density. Probability density is the derivative of probability. So we can write the density of y with respect to probability of y. All right, we can do the same for x. So now we can relate the two. Probability of y is the same as probability of x with respect to y because of this equation. So I just replace the numerator with this. And then we use the chain rule. We first find its derivative with x, and then we find the derivative of x with respect to y. And when I do that, I see that the derivative of this with respect to x is just this, where I've replaced x with y over a times dx dy. So what's dx dy? If x is equal to, if y is equal to ax, if y is equal to ax, what's dx dy? What's dx dy? 1 over a. Yes. Very good. All you have to do is look at your notes. OK. So what we have now is a relationship between the random variables x and y and a relationship between their probability distributions. So if y is equal to ax, then the probability distribution of y is 1 over a times probability distribution of x, where x is replaced with y over a. Let me show you what that means. All right, suppose x is a normally distributed random variable. So by normally distributed random variable, it means it's a Gaussian with mean mu and variance sigma squared. A normally distributed random variable with mean mu and variance sigma squared. So here it is. That's a normally distributed random variable. So when I say y is equal to ax, what I mean is that the probability distribution of y is 1 over a times probability distribution of x. So I have 1 over a in the front, probability distribution of x, which is here it is, but x is replaced with y over a. So probability distribution of y is this quantity. So these are just equations. Now let me show you some graphs. So make it a little bit more sense for you. All right. So here's our relationship. Here's the distribution of x. So say x is a normally random variable. X has a mean, has some variance, and here's its probability distribution. Okay? That's x. But we know y is equal to ax. So say y is equal to 3x. So what does that mean? For every x along that x-axis, you multiply that by 3. And then you find its probability distribution. So what's going to be the mean of y is equal to 3x? 6. Here it is. That's what it's going to look like. Notice that the y-axis, right, it's been scaled. That's what the left side of this equation is doing. That's the distribution of y. So what if y is equal to 1/2 x? What's going to be the mean of y? Y is equal to 1/2 x. Here's x. Here's its probability distribution. What's going to be the mean of y? 1. Just squishes it. When you squish it, it also makes the height rise up. Does that make sense? Do you see what's going on? Now, why am I doing this with you? Why are you being forced to learn about algebra of random variables? Because the hypothesis is that the time it takes to reach threshold is related to a random variable. And we want to know if that random variable is somehow changing from trial to trial, how would the distribution of the reaction time look like? We want to have a derivation of that. All right. So here's our equation. T is equal to x star minus x0 divided by r. So we want to know is that what's the relationship between probability distribution of t and probability distribution of r. So the example I showed you was a times r, right? It was a linear. This is not linear. This is dividing by r. So I need to show you what you do with algebra of random variables when you divide. Okay. So, you know, we want to understand where does this come from. Okay. So y is equal to 1 over x. Now let's look at that. If we have a random variable x and if we have a random variable y and they're related to each other this way, and if we know the probability distribution for x, what's the probability distribution for y? We're going to do the same thing. So we're going to pick x, of course. X has to be bigger than 0. It's on this axis. And we're going to look at the probability of y, capital Y, being less than some amount, little y. Well, that's going to be the same as x being bigger than 1 over y. And so the probability of y being less than this is the same as 1 minus this probability, which is this part, which is written here. All right. So we have a relationship between probability density, the probability of y and probability of x. And here it is. So now what we do is that we take the derivative of this and by taking the derivative, we have the probability density relationship between these random variables. So here's our equation. We take the derivative of the p of y with respect to y. That gives us the density of y, the probability distribution of y. And to take the derivative, we use the chain rule. We take the derivative first with respect to x, then dx dy. And dx dy here, because y is equal to 1 over x, so right, so we have y is equal to 1 over x, so dx dy is minus 1 over what? Y squared. Very good. All right. There it is. OK. So that's our relationship. The probability density of y is 1 over y squared times probability density of x, where x is now replaced with the variable 1 over y. OK. So now we can write the probability distribution. So we have this relationship between t and r. The probability density of r is a normally distributed random variable with variance sigma squared and mean mu r. So this is how r is going to change from trial to trial. Sometimes it's going to be shallow. Sometimes it's going to be steep. And it's going to have a normally distributed random variable. And so given our result from the previous slide, we can write the probability density of x. And probability density of x is going to have this shape, which I've basically plotted for you here. So here's the result of our probability distribution associated with the reaction time. So if your rate of rise is normally distributed with some mean, sometimes it's high, sometimes it's low, the distribution of the reaction times is going to have a tail. And that's going to be, here's our equation, which we saw. OK, so now what if we consider the alternate hypothesis? Maybe the reaction time changes that we're seeing isn't because the rate of rise is a random variable. Maybe the threshold is a random variable. What about that? Could that be the reason why you see reaction time distributions that are sometimes short, sometimes long? So what would that look like? So here's our rise. Say the rise is always the same. But sometimes this threshold is here. That's its mean. Sometimes it's low. Sometimes it's high. So there's threshold that has variability. So if that's the case, if it's down here, then you're going to get to that threshold soon. If it's up here, then you're going to get to that threshold late. So here's the range. And here's the mean. And you notice the part to the left of the mean is exactly the same as the part to the right of the mean. So if the random variable that is changing is the threshold, the distribution will not be skewed. Let me stop for a second, see if you have any questions. OK. Math is such a beautiful thing, you know, because once you make inference based on mathematics, you know, there's only one answer. Now, of course, it doesn't mean this is how the brain works. But at least we can make arguments based on mathematics that says if this was your model of how you reached the decision, and if you imagine it having two possibilities, that the rate of rise is what's variable or the threshold is what's variable, the evidence that you've collected, the reaction times that you collected are consistent with only one of those hypotheses, that it's the rate of rise that's the variable, not the threshold. OK. So, and this is what this basically shows you, that you end up with probability distribution of the reaction time that's just a normally distributed random variable, not something that's going to be skewed, like I showed you. So this is what happens if you vary the threshold. All right, so let me summarize what we have. It takes time to start a movement. Latencies have a skewed distribution. It is thought that the movement latency is related to a decision-making process in which merits of an action are accumulated, rising toward the threshold. And normally distributed rate of rise coincides with a skewed distribution of latencies. And normally distributed threshold coincides with a normally distributed latencies. Because movement latencies are skewed, it appears that they're due to a process where merit of an action is a random variable integrated till it reaches a constant threshold. So that's the model of how decisions are made. You have something that is accumulating evidence, and that accumulation of evidence has to reach threshold until the action is committed, and that could be the random variable that causes the distribution of the reaction time that we've seen. Okay, so now that we have some set of mathematics to think about what's happening in the reaction time, let's look at some data to see how the things that we've been talking about, like reward and effort, alter that reaction time. So the left part of this data that I'm showing you are from monkeys. So what's happening is that they're making saccades, and sometimes they get reward for their saccade, sometimes they don't get reward. So typically in a behavioral animal lab, the animal is deprived of something, in this case say water. And so they're motivated to make movements. They're motivated to work, basically, for their water. So the animal makes a movement, and they're going to get water for it. And sometimes there's a group of targets where they make a movement toward, where they're always going to get reward. When there's another target, when that's presented, they still have to make a movement toward it, but they're not going to get any water. Why do they make the movement toward it? Because that task has to be completed before another one that's given where they get water. So just a few drops of water, or juice. Oftentimes it's juice that they get. So what you see here on the left side of this figure is that you see that the reaction time is higher when the reaction time is shorter when they're going to be rewarded as opposed to when they're not rewarded. So data tends to be left of this identity line, which basically says that you know, I think I have this mislabeled. Let's see, does that make sense? Yeah, so I think this is non-rewarded block. This must be the rewarded block. Because oh no, I'm sorry, this is peak speed. I apologize. I'm just misreading my own plot. I apologize. So this is the velocity of the movement, and here's the latency. Whew. Okay, so let me step back. Let me start again. So they're measuring both the reaction time and the speed of the movement. So what's plotted on the left side is the speed of the movement, and what you see is that the speed of the movement is higher for the saccades when they're rewarded as compared to when they're not rewarded. So that tells you that the movements are more vigorous when there's reward. But more interestingly for us is that the reaction time. The reaction times are shorter when the movements are rewarded versus when they're not rewarded. So you see it here. So these numbers are smaller than these numbers. So latency in the non-rewarded block is longer, which means that basically the more rewarding the stimulus is, two things happen. The sooner you make the movement, the more vigorous that movement is. And this is data that we saw on Wednesday. You see that the saccade itself is more vigorous when the stimulus is more rewarding. Okay, so reward makes it so that you have an earlier movement and you make a faster movement. What about effort? Well, you can make saccades that are short, 5 degrees, 10 degrees, and you can make saccades that are long, 40 degrees. And you can see how long does it take before you start the movement. And so if length of the movement, which is basically the distance that you have to move, is some measure of effort that you would have to put into it to get some reward, the reaction time tends to rise as the effort tends to increase. The more effortful the action is, the later that movement is produced. Does that make sense? Okay. So perhaps latency is related to utility. So remember, we had this idea that something is integrated until it reaches threshold. And if that thing that's being integrated has a high rate, it's going to get there earlier. If it has a low rate, it's going to get there later. But what is this rate that we're talking about? Well, remember, we had this concept of utility. And our concept of utility is a rate. It is reward minus effort divided by time. So it's a rate that we're talking about when we talk about a utility. So imagine now that during the decision-making period, during the reaction time, you are integrating a rate that's proportional to the utility of the action. So if your action has high reward, then that utility is high. You're integrating a variable that's large. Whereas if the action that you're going to be performing has low utility, the integration is of a rate that's small. It would reach threshold later. So now we're going to connect the concept of utility with reaction time. Does that make sense? Do you see the story? How it's evolving? Okay. So this was our utility. Utility is a rate. Rate is being integrated to reach threshold. And so say that you have low reward. Here's the utility function as a function of duration of your movement. So the duration of the movement is optimum here. But if you increase my reward, then the peak value of my utility rises and my duration of the movement becomes less. So this is the duration, which has to do with vigor of your movement. But the value of the utility, which is this rate, is getting larger, which means you are integrating something that's getting larger, which means you should get there earlier, which means the reaction time will be sooner. So as you increase reward, the reaction time should become sooner and the movement should become more vigorous. All right, that's T star. So what we're going to assume that the rate of rise of this variable is a normally distributed random variable where its mean is the utility at the optimum duration. So we had a function that described our utility. We have an optimum duration that maximizes this utility, T star. And now suppose that the rate of rise of your decision variable is proportional. It has a mean that's the utility evaluated at T star. So as you increase reward, you increase the utility of that action. And that means you're integrating a rate that's higher, and you should get there, move there sooner. So one can do this with reward, like we just did. So you can have low reward and high reward, and then you can compute the reaction times for each one of those actions, as well as the duration of the movement. You can do this with effort. You can make it so that you have a distance to move, and you have a small distance versus a large distance, and you can compute the reaction time distribution for each one of those. Okay? And we can do an experiment. We could bring somebody to the lab and make them perform movements, but then add this inner trial interval. So they make a movement, but then they have to wait until they make the next movement. And so by doing so what are we doing? We're adding a time to this denominator. And we're asking them to make a movement after they waited. Waiting is like punishment, right? Because it's devaluing your actions. This is the analog of when you were a kid and you got a timeout. That's what a timeout is adding time to your denominator without giving you any reward. And so that's reducing your utility. Okay, so when you add this Q to the denominator, you should slow the movements. People should start making slower movements, and they should make their reaction times longer because you're reducing the utility of their movements. And that's exactly what we're going to see is what happens. So if you add 1 second of inner trial interval, you're going to have some utility. 2 seconds, the utility is going to fall, and the movements are going to become longer in duration. And here's the probability distribution of the resulting reaction time. So if you make somebody wait before you allow them to move, you should make it so that when they are told to move, they will move later and they will move slower. That's what the theory predicts. And one can go and measure these things, and that's what happens. So if you take somebody and you all of a sudden make them wait before you allow them to move, and then gradually change the amount that they have to wait, what you will see is that it slows their movements and then gradually brings them up. Their reaction time changes in the opposite way, and if you do it in the opposite way, so if you make it so that they don't have to wait, then their movements become more vigorous and their reaction time becomes sooner. So these are some of the manipulations that one can do to affect the utility of movements. Weighting is one of the most powerful ways that you can reduce the utility of their actions. Reward is a way to increase the utility of their actions. Effort is a way to decrease the utility of their actions. These things should influence, based on the theory that we've been talking about, their reaction time as well as their vigor. All right, summarize. It takes time to start a movement. Latency has a skewed distribution. It is thought that the movement latency is related to a decision-making process in which merits of the action are accumulated, rising toward the threshold. It's just like when you're imagining a decision. You're making a decision between doing something and doing something else. During that period of decision-making, you're considering the evidence of the goodness of each possible actions. You accumulate that evidence. Once it reaches threshold, you commit to it and you perform that action. A normally distributed rate of rise coincides with a skewed distribution of latencies. Here, what we conjectured is that the rate of rise may be proportional to the utility of the movement. So, if the utility goes up, the rate of rise should go up. The utility increases, the rate of rise should increase, which means that you will move sooner and you will move with greater vigor. Increased effort has the opposite relationship. And adding a wait time between actions is like adding a time in the denominator. All right. Hope you have a good Easter. Thank you for coming. I'll see you Monday.